I'll give you a bit more of an introduction in a moment, but before I start, can I just do a bit of a straw poll to find out what sort of audience I'm talking to? Who here is an engineer? Yay, I'm in company. Okay, and who here is in business and strategy? Okay, cool. I hope this will be interesting, probably more on the economics side a little bit further on, and so on. Anyone else from different groups, analysts and so on? Okay, cool. That's good. Right, so a little bit of background. My name's Don Robinson. I've been writing, most of you will probably know me because I've been writing for Stream and Media magazine since 2002. These days I write more sort of wacky pieces looking at trends and where I think the industry's going and so on. Partly because my day job, I run a software company which we deliver a sort of microservices stack for doing high availability live streaming. Under the name of Ideas. We deliver, probably the most notable thing we do is we deliver about 70% of the world's financial news for clients like NASDAQ West and so on and so forth. But we also do 40,000 live events a year for DAZN, where we create the mezzanine streaming infrastructure, the mezzanine encoding and the remote commentary set up for them. So usually fairly specialized projects which are looking at high availability live streaming. So I can talk more about that later, but I'm not going to now. I'm going to talk about my favorite little kink. Some people like porn, some people like sports, some people like fishing. My kink is IP multicast, and I've been into it for a long time. So the very first thing I'm going to do is I'm going to correct a mistake in my own slide presentation. Let me just move the mouse. I billed this as 31 years because from memory, I'd remembered the number 1988, and so I had that in my mind that was actually when IP multicast was first defined. My mistake was it was actually RFC 988 where multicast was defined in 1985, so actually it should be 34 years of IP multicast. So before we begin, there was a little error in my writing. So Steve Deering introduced the idea, or introduced the multicast extensions to IP in his 1985 RFC. In 1989, he went on to refine that with the host extensions as well. So we date IP multicast from this RFC. And I think it's important to understand or to establish a common definition of what multicast is and what multicast isn't. So what multicast isn't, despite some rather interesting marketing things that I've seen over the decades, multicast doesn't, to me at least, mean simultaneously broadcasting on traditional broadcast and as a stream and on whatever other delivery you want. Multicasting, or IP multicasting specifically, means sharing packets. It means sending packets to multiple receivers, but in one data transfer. So in the audience here, who of you guys are using IP multicast? Okay, a few of you, okay. So I guess you guys are running either large enterprise networks or you're involved in backbone CDN services. Okay, a few nods, okay. So what we've got going on here is, in the top we see a typical, let's call it, an HLS, a dash stream going on, a unicast stream going on. And for every recipient on the network, we have to send a copy of the datagram, a copy of the packet, okay? So as you get more and more users on the edge of the network, you end up with, you could call it origin crush. You end up with a lot more calls back to the core of the network. So you get a directly scaling cost in your network utilization as you grow the edge network. More users, more data going on, more origin crush. You need to have some sort of reverse proxy and some sort of scaling in this core to be able to deal with that scaling. And that's why every packet you send over a CDN generates you a bit of billing. Multicast is a different approach. In multicast, the basic principle is you have end users joining groups, subscribing to broadcasts. And these are selective broadcasts, which was the original name of IP multicast. And the selective broadcast is only replicated over the routers where there are subscribers, but it's replicated rather than having to be generated at the origin. So if you're sending a live stream, it's particularly good for live streaming. If you're sending a live stream, you send one packet onto the network, and that packet's replicated on the egresses of the router where there are subscribers. So it doesn't flood the network, well, it can, and we're going to go on to that in a minute, but it doesn't flood the network. What it does is it extremely efficiently forwards those datagrams out to the edge while preventing origin crush. So in theory, if the internet was multicast enabled, I could plug my streaming box into my internet connection and I could stream to everyone on the planet, which would be great. It would save a lot of live streamers a lot of money. It would put a lot of live streaming CDNs out of business. This would also be a good thing. Well, maybe not. Multicast, and notice I haven't prefixed it with IP here. Multicast is available in all sorts of network environments without any routing protocols, without any group management top end. So hybrid fiber coax networks prolifically use multicasting to deliver IPTV. It's probably one of its most successful use cases. Your Ethernet switch in your office, that will support multicast. If it doesn't, you should be replacing it because it's probably more than 25 years old. So Ethernet, all you do is you prefix your first bit with a 1, or in IP4 terms, it starts with 224 dot or any number higher, and that says to the Ethernet router, this is a multicast packet. I'm going to forward it out to the multicast subscribers that want to receive it. But IP multicast isn't quite so simple. Let's look at how IP multicast sort of developed in its early days. Now, if you've read anything about multicast, you've probably heard of the M-bone. Any nods in the audience? Yeah, there's a few nods. This is good. Okay, so the M-bone was essentially a set of GRE tunnels, VPN tunnels, connecting all sorts of disparate and originally academic and then latterly enterprise, commercial enterprise networks onto a network where they were trying to deliver video conferencing. Very simple. So it was an attempt to deploy multicast within the internet, but it was like an overlay network, a private set of VPN tunnels and so on. To get the VPN connection, to find a peer or a transit point to connect that VPN through was up to you. There was no QoS on that, on the M-bone and so on, but it did ultimately allow multicast to flow around that virtual delivery network, if you like. In the early days, the M-bone used a protocol called DVMRP, Distance Vector Multicast Routing Protocol. It discovered where there were subscribers by flooding the networks. So, I skipped a part of my own slide there, but you can see DVMRP was the original multicast routing protocol, and it would flood out onto the network saying, I've got a live broadcast, I've got a live transmission going on, I've got a multicast coming onto the network. Does anybody who wants it, this is where it is. So it would announce a session description protocol, which would list all of the available multicasts. Clients would go, oh, I want to listen to that, and they'd effectively tune in and passively receive that data. And then to discover new members of the multicast group, periodically, DVMRP would flood again. Do a little broadcast, say, anybody else want to catch this multicast? That would go across the whole network. Subscribers would join, and that was great. But there were problems with DVMRP and the flood and prune protocols, because those broadcasts would sometimes go back round a routing network, and if you're an old school audio engineer, in effect you'd be getting a feedback loop, and that would cause a broadcast storm on the IP network. So I remember working with Cello Broadband, part of UPC, in 96, 97, to do some experiments to push out some basketball experiments, basketball streaming out onto the Cello Broadband network. And the CTO was really quite annoyed because these broadcast loops were going around, broadcast storms were being created within his ISP network. State in the routers was going crazy, and effectively he was flooding his own network and creating all sorts of capacity problems on his network. The only way to clear that was to reboot the network, which never makes any CTO happy. So they had to shut the whole network down to clear the state, bring it all back up, and he never wanted to talk about multicast ever again. That story was replicated prolifically across the internet, and that is why the internet isn't multicast enabled today. Because CTOs from that era effectively multicast gave itself a bad name. And if you talk to CTOs, they said, oh, it's all very complicated and it messes up your network and we can't deploy it. So multicast hit this screeching roadblock in the sort of late 90s. along came core-based trees originally. So a chap I worked with a lot called Tony Bellardi wrote core-based trees for his PhD thesis in the mid-90s. Core-based trees effectively evolved now, and those of you who are still working with multicast might be much more familiar with PIM sparse mode and PIM SSM. PIM SSM really being the dominant multicast protocol that's deployed out in the networks at the moment. And this was, this CBT and PIM sparse mode require explicit joins. So if you want to join a stream, you transact a little bit more like you would with a unicast. You kind of explicitly go back to a rendezvous point. You say, I want to join this stream, and the routing path is worked out, and you get the stream. But there was no more flooding. So the possibility of doing a broadcast storm was taken away. And what these protocols do, core-based trees, PIM sparse mode, PIM SSM, is while within a LAN you can multicast and you can receive the multicast, it gets more complicated when you go across a router. The router has to know which of its egress routes have subscribers downstream to create its tree. So the routing protocols, that's what their job is. They sit on top of the network and they manage the handoff between the routers to say, okay, we've got a subscriber downstream here. We've got 14 hops all the way back to the source of this multicast. So we've got to set up a routing tree so that we know where the subscribers are and we can manage that tree efficiently. Sitting on top of PIM sparse mode or PIM SSM, you need a group management protocol which manages the subscription process. And the group management protocol stores state in each router, and it's basically a map saying we've got subscribers on egress 2, 3, and 4, not on 5 and 6. So maintain that in state, and every time you get a packet, if it's a packet for any of those subscribers, forward it over all of those egress routes in one transaction. So as IGMP itself has evolved, that's caused another sticking point for multicast. IGMP wasn't for a long time widely supported in routers, domestic broadband routers and so on. Actually, that's probably a bit of a lie. It was, but it's turned off. So it's not configured. There wasn't a strategy like, say, there is with DNS, John Postel's DNS, where he created a whole load of IP addresses and mapped them to domain names. There wasn't a single coordination for multicast address allocations, just to sort of rule anything above 224, the class D address space in IPv4 terms, is reserved for multicast. That actually goes back to why the first bit is 1 in Ethernet, but that's too much for now. So IGMP was shipped, but turned off, unconfigured. So that's why when you tried to join a multicast through your ISP's broadband router, it couldn't talk to anything in the ISP. It couldn't talk to anything further upstream because there just wasn't a configuration for that workflow to actually establish the routing tree and create the flow. IGMP itself has also evolved, so even though there are quite a lot of routers out there with IGMP v2, which allows you to connect to PIM sparse mode streams, PIM sparse mode wasn't source specific, so you could end up getting the wrong stream. It didn't have a security model. You couldn't be specific that you wanted to connect to one stream. And it's important to note that when multicast was first introduced, it was introduced by academics who wanted a conference. It wasn't thought of. I remember meeting Tony, some very random series of events, but I remember meeting Tony deep in the UCL. I don't know if Nermine's here as well. She was, anyway, who was deep in the UCL community, who were really pioneering all the multimedia tools that have evolved into the stuff that we in the streaming media community use today in the early 90s. And when I went to talk to Tony, I said to him, have you realized what this means to TV and radio? In the late 90s, and he was like, well, what do you mean? I was like, well, if you can scale streaming, live streaming on the internet, then TV and radio is going to move to the internet. And he sort of looked a bit, oh, I hadn't really thought about that. I was trying to conference with my colleagues. So there was this sort of strange dissonance between where they were going with this amazing technology and what they were and the application that they were trying to build it around. So anyway, PIM sparse mode was really, after that era, PIM sparse mode emerged to specifically look at the one-to-many use case, specifically seeing IPTV and streaming becoming important and commercial models building up around it. So we needed a security model which didn't, for example, allow the Rolling Stones stream to be crashed by, somebody remind me, the band that crashed the Rolling Stones stream in 93 or 94 or whatever it was. So IGMP, which enables that PIM sparse mode layer, evolved, and obviously there are probably many routers out there which have IGMP v2 support, but in terms of our industry, the really interesting one, which is IGMP v3, is much less supported because there's more legacy infrastructure out there. There's another challenge that Multicast faced, and that's down at the bottom here, the inter-domain multicast routing problem. So it's all well and good to go around an enterprise with routers that are under your control and to multicast and to establish your multicast model in that environment. Well, what happens when you get to an internet exchange point? And you're trying to deal with crossing the exchange point when you're doing BGP peering. So, oh, I've skipped one there. Oh, it's still visible. So around, I can't remember the exact year, but it's about 99, 2000, Tony and a wide range of the community in the IETF started working on MBGP, Multicast Extensions for Border Gateway Protocol, which was looking at how you forward multicast at an inter-ISP, an inter-domain level. So this was a direct response to the IDMR problem. And actually, it's not that complicated to set up. Multicast peering, it's not that difficult. Certainly not for anyone who's playing with BGP. You engineers in the audience, if you understand BGP, MBGP's not that much more complicated. It's a bit unusual, perhaps. It's not that much more complicated. And MBGP allows you to start a stream in one ISP, take it up to the exchange point, peer into the next ISP or the next AS, and forward that down to the end users in a third-party AS. And the lack of MBGP support in the internet is another one of the key sticking points that Multicast has faced in scaling itself out. To bypass that, a lot of people did set up GRE tunnels going back to the old M-bone model to get Multicast to flow through transit rather than through peering. So you could have an enterprise network in one city, an enterprise network in another city. You could set up a GRE tunnel, and then you could put a Windows Media multicast stream running on one enterprise network, and all the media players in the other network would be able to watch that stream with only a single copy of the stream passing between two enterprise networks. And still to this day, with my day job hat on, we still deliver tons of Windows Media, and I'm hoping that's going to generate a bit of a laugh, because I think we're probably one of the last organizations in the world doing that, but that's because we do a lot of financial news, and the NASDAQ and the West use case is to hand off town halls, hand off financial announcements into the enterprise networks, and one of the ways we do that is actually directly unicasting to a Windows Media server, sometimes an NT4 box, that's in the corner of the enterprise network. That's a good expression. and everybody in the enterprise network can turn on their TV, and there's no massive spike and load on the enterprise network, and you can have 30,000 people watching a stream with a single stream going into the building. There are obviously other ways of doing that that have emerged. So one of the things we looked at was the automation of deploying GRE tunnels, and in a project that was rather charmingly named Project Goldfish, because we were trying to hide it from one of our shareholders in my old company, which I'll talk about a little bit more in a minute. We came up with what is now called Automatic Multicast Without Explicit Tunnels, AMT. On pitching that around the industry, a lot of people liked the idea, and Octoshape, Flash, and various other people got right into the idea of deploying an AMT model. And what you have is essentially something that sets up tunnels on the fly. The first client looks on the network, hasn't got the multicast, so it creates the tunnel and introduces the multicast to the network, and that first client on the network then forwards it out to the other clients in the environment. So there's rather charmingly called P2P or peer-to-peer. The old school engineers would call it application layer multicasting, because it's all done in layer 4. It's not done down at layer 3. And peer-to-peer is a usable solution if your network is under your management and you can control the quas on the network. But peer-to-peer doesn't have quas inherently, so it's very challenging to roll out a peer-to-peer service where you're trying to offer a premium proposition to customers, where you might be underpinning that with some SLA that when they pay you $20, they're going to get their stream. It works, but it itself doesn't allow you to really deploy commercial models at scale. Oh, I skipped over IPv6 multicast. By the time IPv6 was defined and rolled out, multicast was inherently much, much more straightforward in an IPv6 environment. And that's why today, if you look at the core backbone chunks of the internet, they prolifically use multicast. Most of those networks are IPv6 centric. Global mix. So 2001, Tony and I decided, I'd been webcasting since the mid-90s. I did my first IP transfer of imagery off the back of some CCDs that were on the back of the William Herschel telescope in 1990. And we were creating time lapses of binary stars. That's a different story for another day, but it's a reasonably interesting one because I date my own involvement with IP and streaming back to 1990, which is probably way longer than most. By the time Tony and I were trying to work out how to multicast enable the internet, we thought it would be a good idea to actually go and get lots of streams aggregated and to create some sort of propositional case to ISPs and networks to enable them to support multicast because we had content. So we set up the Global Multicast Internet Exchange. And we were very lucky. Tony knew, oh, I've gone blank. Obviously better than me. Tony knew Keith Mitchell, who'd started the London Internet Exchange. Keith had just left Links to set up Exchange Point. He was very enthused by the work that Tony was doing on MBGP. And so he gave us half a rack and a router. Tony implemented MBGP, and I'm kind of proud to say that actually that then folded back into Links and still exists as the London Internet Exchange multicast peering network. It's not extensively used, but it still exists 20 years later. Global Mix was a really interesting proposition for anybody who's looking at multicast. And I'm really pleased that in many of the sessions over the last 48 hours, I've heard multicast come up as a term, probably more than I've heard it come up as a term for a decade or so. And we'll come to some of the reasons why that is in a minute. But the key challenge that we were addressing was trying to deliver multicast directly to ISPs and educate the ISPs on how to forward that, enable IGMP v2 or v3 right down on their domestic routers to pick up our clients' content and deliver it. Now, obviously, those of you who, I'm hopefully talking to a few old schoolers who were familiar with Windows Media, it had a good system for failing over. If you couldn't find the multicast, then you'd fail over to unicast. So we could always commit to our customers that we could deliver a stream. But wherever we could move that streaming onto multicast, we became more profitable. And as a tiny little 5-man CDN based in the UK, that was really quite an important element of our survival. So we acted as an aggregation hub. We went to lots of radio stations, lots of TV stations. 2002-03, we started bringing Classic FM online. And by 2008, we had over 600 radio stations and probably 2-3 dozen TV channels broadcasting over Global Mix. Probably at peak, 15% of our traffic was IP multicast to domestic home users on effectively the open internet in the UK, which is, I think, 15% more than anyone else has ever achieved. But we had a problem. And going back to my story about Cello Broadband, what was happening was CTOs would come in. We would work with an ISP for 2-3 months to help them get this service rolling. We'd go in and we'd say, look, our peering point is, or our transit into you is getting jammed up. This is a business case to justify turning these 2,000 simultaneous streams into one. This is going to reduce the inefficiency on the peering and the transit point. They're your customers, which is a really nice part of the discussion. They're your subscribers that want this service, so let's do this better. And we'd sometimes get buy-in. The CTOs would give us their support. We'd go in, we'd roll the IP multicast out to the end users. And then there'd be a policy change. And one of the other old CTOs from another ISP would come in and go, what are you doing multicast on the network for? And boom, they'd turn it off. Our peerings would suddenly spike. All the transit would go up. And it was challenging to maintain that. We obviously offered other services within Global Mix, DRM, conditional access services. We did some quite interesting things with IP Multicast and conditional access. And the core central proposition, which differs from, I mean, I'm sure some of you would love this today, but the core central proposition of our CDN was to deliver your TV channel online as a flat fee. Doesn't go up or down. And that was our risk game within the whole thing. But we just said, you know, it's £2,000 a month to deliver your TV channel on the internet. It doesn't matter if you have 10 or 100,000 users, it's going to be £2,000 a month, which I think would be a panacea for a lot of people doing live streaming here today. And it was obviously, you know, an interesting USP for us. And a lot of the customers came to us and thought, oh, you're kind of good with this streaming stuff. We've also got a whole ton of video on demand and audio on demand we'd like you to host, so can you host that as well? And that was great, because it meant that our unicast streaming, as we became a larger and larger wholesale buyer, at the time, 2008, we were delivering 150 million streams a month. By comparison, YouTube at the time was doing 1 billion streams a month. So that's kind of, we were quite in the game at the time. But of those streams, probably 60% was unicast VOD, or audio on demand. And that buying power was important, and it opened up a can of worms, the unicast problem here. Because when we turned on a big ISP, and suddenly 15% of those 15% of our live traffic went oof, multicast, our unicast buying power fell, which meant that all our VOD and audio content delivery costs went up. So strangely, by becoming efficient, we became less profitable. And I learned something very important about the telco industry, and we see this prolifically in our industry. Telecoms networks are really good at telling you that they're congested. They're not. And I challenge a telco here or anywhere to come and prove that they're congested, that they don't have an almost infinite amount of dark fiber that they can just light up terabits and terabits of capacity on. So telcos themselves love to sell congestion and scarcity because it adds premium to their network. And this is a big problem. CDNs, they're all, oh my God, how are we going to deal with all this traffic? If they tell, that's really easy, we've got tons of capacity, you'd struggle to pay them money. It would be much harder to invest in that if they're not solving some problem for you. So strangely, we ran into this economic problem where our raison d'etre, our whole motive of delivering IP multicast into the internet, counterintuitively, was actually buggering up our video on demand and our audio on demand delivery business. And still to this day, that economic challenge is a problem. The CDNs, you look at this maybe simplified paradigm shift of moving TV entirely online and turning off the traditional broadcast models. And of course, every CDN and every telco out there is going to go, oh my God, our networks are going to be flooded and saturated. Well, not if you turn on IP multicast, certainly for live streaming. You're going to see one stream across your network. But if they told you that, and if they did that, they wouldn't be able to charge you hundreds of £1,000s a month for your unicast delivery, so it would put them out of business. That's a fundamental structural problem in our industry. The other problem we've had, I mentioned earlier, was coordination. There was no multicast lookup table. There was no allocation of 239.1.2.3:8080 or whatever the port may be was tied to, I don't know, NASA's live stream or whatever, or Fox News or whatever it may be. There was no coordination, which would have made the inter-domain multicast routing challenge much easier. I think today, if a large CDN, nominally Akamai or something like that, actually stepped up and said, look, we're going to start making multicast available at our edges, and they're going to create an address map, it would make the lives of the ISPs and the telcos more straightforward because they'd know what they were forwarding into their networks, and they would have a little bit more involvement with that decision. But at the moment, because there is no centralized sort of DNS-type model to coordinate things, multicast is all ad hoc. People just grab addresses, and it's all very private, and it becomes very difficult to do an inter-domain multicast routing model at scale. The other challenge obviously was Flash. Now, Flash really messed up Global Mix because we'd originally started doing pre-roll advertising in 2003 because it obscured, it was a little unicast that obscured the 8 to 10 second delay while we joined the multicast. And it then just happened to become a really nice spot to sell advertising in. So the live streamers would go, actually, let's start doing pre-roll. And as they got more and more hooked on pre-roll, the advertisers started demanding that even those pre-rolls started faster, so they'd be playing before you scrolled down the web page. And of course, at that point, Flash appeared. And Flash, being simple RTMP or session-based unicast protocol, it could start very quickly. And interestingly, it's just a sort of side comment here, but interestingly, at that point, the adverts would start, and after the advert had played, the content providers would crush the hell out of this live streaming because they actually didn't want to pay for any live streaming. They just wanted you to see the advert and then, frankly, hopefully reload the web page and watch the advert again. But the content behind the advert was really almost an afterthought. But the ad industry was driving things by 2008. As a business, we'd hit the economic problem of becoming more efficient. It was actually costing us money. And we'd hit the other problem that the market was moving to Flash because of this fast preloading, pre-roll advertising. We were Windows Media based, we were appliance based. I had an epiphany, well, also we were in the face as a small UK company with Akamai Limelight, all the big CDNs arriving, and their monthly office budgets were our annual turnover. We couldn't compete. I saw the writing on the wall. I also saw that virtualization was going to be absolutely critical for businesses in the future who were in our situation and needed to rapidly change. So my team went off, and they're all now working for the big CDNs or big broadcasters. I went off and started my little microservices company to try to deliver virtualized encoding and so on. So I strategically went a different way. But the challenge of formats, watching from that point in 2008, 2009 forward, all the protocols on all the formats that are being used for streaming are all HTTP based now. That's great because the CDNs find it extremely efficient to commoditize on one technology. They've introduced problems like latency, which we all had solved. You know, RTMP was really good for low latency. In fact, our RTP was really good for low latency. I know those go back 20, 30 years. So all this endless talk in the industry at the moment about how do we solve the low latency problem, it's so frustrating because we had it solved 20 years ago. And we then decided we've got to do everything as HTTP, and we kind of log-jammed ourselves in this space where we now have, we think of low latency as 4 seconds. Anyway, an interesting challenge. And the other challenge, which I've already mentioned, was IGMP v3. And getting that rolled out, getting that supported, getting that turned on. But multicast isn't dead. It's having a little bit of a renaissance at the moment. Now, if I was going to make one recommendation to go and investigate, especially to the network engineers here who are interested in multicast deployment, go and investigate bit-indexed explicit replication, BEER, perfectly named. Driven by Greg Shepard at Cisco, but many other people have been involved with that. The principle, which you've probably seen in a number of different contexts across the whole computing industry, the principal challenge that BEER sought to overcome was that memory in routers is a reasonably scarce commodity, and filling up the memory of a router with millions of different routing states for where your multicast subscribers are is a complexity and a resource utilization. So the model that BEER's taken is to move the routing state into the header of the packet itself. So when a packet arrives in a network, it says, this is my map for how I want to egress your network into third-party domains or into subscriber networks. So BEER's moved that routing state up into the header of the IP packet and promises to, in my mind, promises to address the inter-domain multicast routing problem in a way that IGMP and the traditional multicast routing protocols haven't. It's still only just been passed through the standardization track in IETF, so it's still quite young, but do go and investigate it. I think BEER is going to be important. I love saying that. We've also got the challenge that adaptive bit rates emerged, and joining a group in a multicast can take a few moments. You've got to do this session discovery, you've got to find your multicast, you've got to join it, you've got to buffer your first GOP before you can render anything. Doesn't lend itself very well to an adaptive bitrate model, but it is possible. The Cable Labs multicast ABR strategy has really gone a long way to addressing that. We were doing something like that, but multi-rate rather than adaptive bitrate, so just having, if you like, several different streams going on at different bit rates and trying to switch between them while we're playing out the last GOP from the previous video, but detecting when to switch is always a headache. I'm glad Cable Labs are doing that now, not me. That was a complicated one, but it's certainly possible. The other thing that, in my mind, I think is probably most exciting is LTE broadcast, EMBMS, enhanced, well, I'm not going to remember what EMBMS is, EMBMS and LTE broadcast. So the high-end LTE fourth generation and notionally 5G networks will be able to support multicast from the RAN out to the end user. Which sounds like a great thing for doing live broadcasting to mobile devices. It kind of solves a problem that certainly in North America and Northern Europe, mobile networks don't really have, which I discovered more from looking at mobile edge compute paradigms. I was talking to Nathan earlier on about this, which is that most masts actually have dark fiber running into them. So if you run out of capacity, it's really cheap. You've got low maintenance switch gear at the edge, and it's actually quite cheap just to light more fiber. So if that backhaul's getting congested, then just add another wavelength. And that solves a problem that's much easier for a telco than adding intelligent compute to proxy data or create a CDN or an edge compute environment out in the RAN. So actually, you then run into scaling issues on spectrum. And the scaling, this is a common problem that ATSC3 faces as well. Your congestion is no longer IP-based, it's actually layer 2, it's actually in spectrum and getting that last mile link out to the access device. So if you've only got radio spectrum which can say support 20 or 30 parallel, 20 or 30 different 20 megabit streams, picking a number out of the air, even if you multicast, you might make that bouquet of content available to all the people who want to tune into it using your combination of EMBMS and LTE-B. But you're still going to hit ceilings in terms of your RF spectrum and so on. So just making LTE-B a way of scaling any live broadcast to any number of consumers over a 5G network is going to run into problems other than IP-centric ones. It's going to run into RF problems at the edge. So it's got some scalability. It's great for things like stadium streaming, which is where you've seen the LTE broadcast demos and so on. But as a true solution for scaling live linear globally across 5G networks, I'm yet to be convinced how that's going to be done. There's also one space where IP multicast works beautifully, and that's in satellite. And I've played a lot with satellite IP, originally using VSAT for contribution for webcasts. Then I built a satellite CDN with Microsoft in 2002, which was doing digital signage updates out to petrol stations, garages, and so on. Beautiful model. And then again, we revisited that with one of the very large satellite operators over here in the US in 2013, building a full sort of edge compute fog architecture over satellite as well. It works amazingly with multicast. It is a big Ethernet switch in the sky. It's an expensive one, and it's difficult to maintain, but satellite has some amazing abilities to solve problems. For example, delivering large quantities of specific streams out to mobile masts where there aren't backhauls. So outside of North America, outside of Northern Europe, satellite really does offer a very viable way of doing heavy offload of lots and lots of live streaming. So don't discount satellite, even though the poor guys in the satellite industry seem to discount themselves at the moment. It's actually a small but extremely potent capability within the satellite space. So again, if you're interested in deploying IP multicast out onto big operator network and deeper than deep edge networks, satellite is still very definitely worth exploring. I kind of talked about RF and last mile scaling, so I think with that, it was intentionally short, partly to allow a few questions, but also partly to make sure we can all get to lunch before the rest of them. So, and with that, I'm done. Are there any questions? Yeah. So you mean in terms of having sort of like you'd get when you launch a big D+ type service and everyone decides to subscribe in the same morning? You mean that type of?
As a user, if I subscribe to everyone, like thousands of streams, I will have basically 1,000 streams DDoSing my routers. So the router that's for me and all my colleagues, but also the building.
So yes, that's not that you won't have that problem, but it's going to be many, many, many times less of a much less of a problem than if it was unicast, because you would have parity between every end user and all the streams passing through your router. Whereas with multicast properly deployed, you would only have one stream, one packet passing across the router, regardless of how many thousands of people were subscribed to it. So you will get a lot of traffic going through your router, but you'll only get one stream per source rather than one stream per destination. So you could argue that that's DDoS, but it's solving quite a lot of the DDoS, or the sort of comparable DDoS problem there. Does that answer the question? Yeah.
So if you congested your link, well, you cannot send stuff out. Whereas here, you subscribe once, and then the stream goes on.
I'm trying to understand that. Let's do that on paper after the session, because I'm trying to work that one out in my head. Yeah. Sorry. Yeah.
So I want to spend a second talking about SVOD versus live.
Okay.
The fact that Multicast is awesome for live because everybody gets the same stream, they get the full play, there's no issue. But obviously, PvP for SVOD has the congestion issues that we were talking about. Is there any kind of a metric that says in today's market how much is of what people are streaming is SVOD, how much of that is live, and therefore how maybe there's another aspect to like multicast that's needed, like say, you know, soon to be launched.
So it's a common assumption that multicast is no use for on-demand. But it is actually quite useful for on-demand because you can pre-position.
Right.
So for the CDN I built with Microsoft in 2003, we were pre-positioning carousels of content out into hard drives in all these garages. And they were just played locally, effectively as a unicast between the computer and the screen, or the multiple screens on site. So multicast does have software updates. It's fantastic for pushing out software updates, which isn't a real-time streaming thing. But you know, if next time iOS goes out, pushes out a big update, if they could multicast it, well, we just sent 13 gigabytes instead of 13 million petabytes or whatever it is. So I think there is scope to focus on IP multicast within the SVOD and the on-demand space, but it's got different models of deployment. You have to be able to anticipate the content. You can't obviously do it in response to a request. Otherwise, it becomes like caching. It becomes proxy serving, and that's something that's probably better done in layer 4 than in layer 3. I don't know if that.
You're addressing the issue
Yeah.
that I was sort of getting at, which was your optimistic delivery
Yeah.
content to be launched. Have you thought, or one of the bullet points you had there was about resilient or higher reliability?
Yeah.
Unicast delivery.
So we use multicast in the enterprise networks for the clients that I mentioned earlier for doing the sort of high availability sports stuff. So the big mantra for ideas is we offer 5 nines availability. And to get that 5 nines, but we've actually got a client who's got 100% availability for nearly 7 years. Not because things haven't gone wrong, but because we have a completely tight strategy for how we deal with that. And central to that is IP multicast. So we're doing some work with one of the big global CDNs at the moment, and they kind of want to do multicast, but their techies are kind of scared of it, or there's some hesitation about it. So the workaround to make up for the absence of multicast introduces much, much more risk to their availability than if they just enable multicast, because as soon as you have multicast available, you can have as many virtual transcoders as you want hanging off that multicast, and if one of them dies, the others have already got it. Or if you've got 2 multicast sources on a network, then all of those transcoders can pick either of those 2 streams up, and if one of them dies, you've automatically got resilience. So multicast is actually extremely good for resilience within that enterprise network environment. So yeah, again, it's another good sort of case of point.
The word that you didn't use was for architecture. So that,
Yeah.
because like on a cloud platform, packet loss is just everywhere.
Yeah, yeah. You can do FairCon on multicast, and you can also do a simple carousel replacement. You know, if you missed a byte, wait for the data to be, especially if you're pre-positioning content, you can ship it. If you lose a few packets next time around, you collect the packets you missed, and so on. So yeah, there are approaches to most of these things. Multicast is, because of the join process, beer might make a difference to this, but because of the join process in PIM sparse mode and IGMP, multicast almost invariably adds, you need to add some buffer, some latency to allow the join to, the routing tree to form before you can even send the packets. So yeah, multicast isn't the best story for low latency, but you know, I don't think there are any good stories for low latency these days. So anyway, any other questions? Yes, please.
Yeah, we used to have our enterprise configured with PIM sparse, did some extensive class D addressing,
Yeah.
everything working.
Yeah.
But because Cisco doesn't enable multicast by default,
Yeah.
we have some engineers go in, switch out a router, forget to do the work instructions, suddenly.
Dead network. Yeah.
And to try and troubleshoot where it's broken was very tedious. Do you know any companies or any multicast tools out there that can help you trace where it's broken?
What's it called? There's some command line tools baked into the Linux kernel, which I can't remember what they are at the moment, but I can grab card, and if I can't remember it, I'll ask one of my colleagues who'll remember. But there are a couple of nice testing tools out which will help you diagnose where multicast is flowing and where it isn't. But you still kind of have to probe in to find out where you can join, but at least it helps you isolate where in the network you've got it breaks down, if you like. So. Again, it goes back to, I think to some extent, if there was that more centralized strategy like DNS has to how you deploy multicast, then I think it would come shipped on, all the multicast routing capabilities would come shipped on in the Cisco and then whatever the routing vendor. It's so frustrating to think that we could just turn it on. It's there, it's already deployed, it just needs to be activated, but there isn't a coordinated way to do that. Because if we could, it would scale live content delivery on the internet so much better. But
Even Cisco, they don't have any really decent tools to trace it.
yeah, yeah.
Frustrating, you know, they used to have that,
Cool, I'm
build that
casting.
beautiful map,
Yeah.
and no way.
And as the engineering skill gets more and more rarefied, it's a complicated decision. HTTP is cheap and commodity and everyone can maintain it. How do you find a multicast engineer who can do that debug? And that becomes a different cost. You know, having a multicast engineer who costs you $300,000 a year to save you $2,000 a month on your routing bill doesn't add up, which is a skills problem in the industry as well. So. Any more questions, or should we do lunch? Let's do lunch. Okay.